Hi everyone, thanks for coming. As you can see here, the title of this talk is Using Smartphone Technology in Geoscience Education, and I'm going to talk to you about some of the stuff that we've been working on during the past couple of years at Northwestern and designing instructive, fun, cool labs for the students. After which they can always have some really nice take-home message and they can relate to. So, teaching geoscience is fun. Yeah, I think we agree on this because we're all here because of this. Uh, so Earth science is great to teach because it has great real life topics. So in Earth science, you always have something really cool happening in the world. Be it some sort of hazard or some sort of geological tectonic phenomenon. You can always talk about something really cool in your syllabus and in your class. Also, it has interesting hands-on examples. You don't really need to, be super sophisticated to teach something to the students. They can always, learn stuff about earth science using pieces of papers and adding two by two, be measuring the period of the oscillations of a pendulum, and so on. Plus, it has not nice outdoor activities. Some of these examples are outdoor. This picture in the middle, for example, with all the smiley faces, was taken during a field trip that a bunch of grad students and faculty and researchers did together during one of the days in a conference in California, where we actually observed the location where the San Andreas Fault ruptured during the 1906 earthquakes, and you can actually see the 3 meters offset as a result of that earthquakes in this image. Also, earth science is easy to relate to. Everyone has some interest in earth science because, well, it's involved during everyday life. It plays an important role in some aspect of our lives, at least. So it's really cool. But how are we doing in the science? How are we doing in teaching the science part? Well, the National Science Foundation, the National Academy of Science, the National Science Council, has a really famous quote. They say, "Science subject matters focuses on the science facts, concepts, principles, theories, and models that are important for all students to know, understand, and use." Well, this is a textbook sort of statements for teaching a class because students have to learn this stuff. They have to know it. They have to understand it, which goes like, their brains have to process the data and they'll eventually have to be able to use it. The chart on the right is a sort of a reconstructed version of what is famous as the Bloom taxonomy. This is made by Rex here at Iowa State, and he's done a really good job at the scaffolding this. So while it's correlating the cognitive process dimension of teaching to knowledge dimension, it's also implying which aspect or which product of these two is actually the most important. So you see on the lowest level, you have the listing, recognizing, summarizing, classifying, and while these are all related different parts of the cognitive and knowledge-based dimensions, you can see listing is less important than classifying, and classifying is less important than carrying out experiments, and they're all less important, less significant than integrating compliance. Integrating what you've learned with what you can do. So how are we doing? From the output of earth science classes, we can actually say, well, we're doing a pretty good job at the lower level of stuff. All the students can identify rocks, they can classify what they've told them, they can provide us with explanations and apply things to in experiments. They can carry out experiments and, do different things. So we're doing good on these. No concern here, almost. Earth science students are also good at integrating stuff with new topics into new experiments, and they're also really good at determining the you know the plus and the positive and negatives aspects of any given topic. So we're doing well there too. Uh, Depending on what teacher is teaching, which teacher is teaching what, students are also sort of efficient in judging, like, evaluating things as a result. And good students are doing well on that aspect. So we're doing fine. But as for the three top cells of this sort of broken pyramid, I'm not saying we're doing bad, but these are the main areas of concern. Students, well, first they will need to be able to reflect upon their personal things, their knowledge, and they have to be able to draw upon what they already know, what they already feel like onto the real problems, and they'll have to be able to design the experiments. They eventually one day they are the ones who should be able to put things together, set projects up, and eventually they will have to create. They will have to use their knowledge to actually be creative, make things, build things out of nothing. So, um, well, people argue. I mean, this is one of the hot topics of research. People argue that, well, these three cells, these three topics come about only, mostly through active learning. There's a famous quote by Helen Batham. She argues that several decades of research support the view that it is the activity that the learner engages in and the outcomes of that activity that are significant for learning. So, the way our brain is structured is that we learn best while we're trying stuff. You learn driving, if you actually drive. You cannot drive your car by passing a course and be all right. So how can we do this? Well, we have to set up activities. We have to set up labs. We have to set up strategies for students to make students do some stuff. Well, in order to do that, what do we need? We need a whole bunch of instruments. We need a whole lot of things that actually can make measurements, because we want our stuff to be on the cutting edge of science. So we need good instrumentation. We also need a whole lot of computational power. Well, the data need to be processed at some point and plotted, and so you need computers. You need good computers. And well, you need training. You need to train the students. You need to train the users how to work with those instruments, how to make plots, how to convert things to things. And well, while this seems really nice, it's expensive. It needs a pot full of money, and not everyone has that money. Actually, very few institutions are willing to just lavishly spend money on these things. So what can we do? Every single one of us, every single instructor, earth science instructor, every single science instructor has struggled with the idea of, like, I want to do cool stuff, but I don't have money. And probably, one of the answers to this really interesting question is smartphones. Smartphones are really nice computers, really small computers with huge processing units. The processing units of a smartphone was only dreamt of by the computers, like, a decade back. And well, it's not just the computational power. They come in with a whole bunch of sensors. They come in with accelerometers. They come in barometer, pressure sensors, thermometers, light sensors, magnetometers. They come with positioning systems, all built in. You don't really have to pay extra when you're purchasing a smartphone. So it's really tempting to at least give a shot at it. Try to do something and see if it works. This is actually exactly what we did at Northwestern. We tried to design instructive, fun labs, something that the students enjoy, but learn things at the same time, and try to achieve those three higher level cells in the Bloom's taxonomy. So we picked two, let's say, famous topics in earth science. Well, earthquakes and measurements. Well, measurements are really important. We added them to the mix because we wanted students to have good grasp of the uncertainties in measurements. So we picked two case studies for these two topics. For earthquakes, we tried to study seismic waves, and for measurements, we addressed a really interesting topic of accuracy versus precision. We set up a bunch of labs in an introductory geophysics class at Northwestern. Seth Stein was kind enough to actually give us an opportunity to actually improvise, to give us a chance to actually do things in the class, to modify things. So what did we do? For the seismic waves, first of all, seismic waves travel through different materials differently. In the Earth, seismic waves travel through different rocks at different speeds. So if you know it as seismic speed of a medium, you have a pretty good chance of saying what kind of a material that is. So seismologists build arrays of seismometers and try to record the waves from different sources. Here I've listed two earthquakes and explosions, but there are many more. So by recording these signals in arrays, we can actually, there are techniques through which we can calculate the speed at different material, the different structure within the Earth, and sort of just like a CAT scan, try to image the layers of the Earth. So in the image on the right here, I've shown like an array which is being towed by a ship, and that ship is sort of making explosions with air guns, and those seismometers that are being towed by the ship, these seismometers are called hydrophones. They're recording the reflections of these seismic waves from the layers inside the Earth, the layers beneath the ocean floor. So it's through these methods that seismologists can sort of determine what the structure and what beneath the ocean floor is, what material is there, and people just find oil using these methods. I usually tell students in earth science classes that these the reflections inside seismic waves from these experiments are worth billions and billions of dollars, because they're well spent. They're used to find oil. So we try to do the same thing in a class. Remember I said smartphones come with built-in accelerometers. Accelerometers are types of a certain type of seismometers that can actually record shaking. So naturally, we use smartphones. We build a seismic array, just similar to what I mentioned in reflection seismology a few minutes ago, and making an array on a phone. We asked the students to pound on one end of the table, and in this way, the accelerometers inside the phones could record the arriving energy. So, like the closest phone to the pounding point would pick up the signal first, because the energy took some time to travel through the table, even though this time was really small, in the order of a few milliseconds. But then the energy would go from one point to the next. So you can see here the signal is arriving, schematically arriving later and later as you go further away from the source. And then we ask the students to identify which phone, what kind, the phone number, the first phone, second phone, third phone, and so on, in their data, and upload the data, which was like a 2-column file, time and energy, like time and the amplitude of the signal, into a cloud space to be available to everyone in a class. And this is the setup of the experiment. So we made an array. Someone started pounding on the table, and here's what happened.
Oh, that was pretty high. That was
Now, remember, the horizontal axis is time, and the vertical axis is sort of distance from the pounding source. So the bottom trace is the closest phone to the pounding spot, whereas as you go up on the distance from the source axis, you go away from the pounding. So it's like you move right in this picture. So you could say, well, I connect these dots, these energy arrivals, and well, the horizontal axis is time and the vertical axis is distance, and the slope of this plot is velocity or speed. And you calculate it, you do the math, and you'll get about 35,000 meters per second, which is really nice. I mean, this is really close to the actual value for the speed of waves and wood, which is what this table is made of. So success, we're doing really a good job here. Smartphone thing works. Now, what else? What else can we do to make our case? The next order of business is accuracy versus precision. So every measurement includes accuracy and precision. Remember, we call a bunch of measurements accurate when they're really close, or the average of those measurements is close to the actual value. While precise, in the case of precise, the measurements are really clustered. They're really close to one another, but not necessarily close to the actual value. So on the right hand side, you can actually see the the bullseye, the targets, and someone's shooting at them. On the top left, you can see a bunch of measurements that are neither accurate nor precise. They're all over the place, so they're not precise and they're not accurate because the average doesn't coincide with the center of the target. On the top right, you can see measurements that are not accurate because they're not close to the center, but they're precise because they're clustered. On the bottom left, they're accurate. The average is sort of at the center, but they're not precise. And the bottom right, you see both accurate and precise. While this seems really trivial and easy to understand, these concepts play, extremely important roles in analyzing data and reporting scientific data. And students sometimes struggle with them. So we try to put something cool together and ask the students to work with their own data, because remember, when someone works with their own data, they will feel more comfortable with the results. So before actually showing our case, let's do an activity together as a warm-up. Let's try to do something with our phones. Everyone in the audience, please pull out your phone, enable the location service in your phone, and what I want you to do is pull up the Google Maps app and zoom in. When that app starts, zoom in on your current location. So you will, when you start the app, you see a blue dot. Try to zoom on it by just dragging the screen outward, and then after you get a really good view, like get as close as you can, just long tap. You keep your finger in the blue dot. Long tap the blue dot, and you'll see that red pin over there. On the top, after you do that, you'll see the geographic coordinates of your point, of that blue point. So the number that starts with 42 something is the latitude, and the number that starts with minus 87 is the longitude. And what I want you to do next is go online to this link and fill out the form. The form is going to ask you about the type of phone that you're using, and just the latitude and longitude from those fields over there. Let's do this together, and we'll brainstorm it later for a couple of minutes, okay? All right, now, so as you saw in the activity, and like how the instruments show up in the final map, it's actually cool. It's really fun for the students to do. Well, we did this, sort of a very, very similar thing to what you guys did here today. We asked them to measure coordinates of a given point, which was the corner of a planter, outside the building that we were having classes in. And well, we told them to do measurements at least 6 hours apart, because due to the positioning of the GPS satellites, because we wanted sort of a different arrangement of the locations of those satellites. And then we asked them to submit their data into an online document, let's say Google spreadsheet, and then try to analyze it. What do we mean by analyzing it? Well, we told them to make these sort of plots and maps. On the left, bottom left, you can see a map view of the same location. Here it's in Evanston. There's the sidewalk. There's the street on the left, and then here you have the stairs and the planter and the buildings. But there's a yellow star. That's the geospatial reference point. We marked that point on Google Earth, and we had the locations. You remember, geospatial coordinates are considered to be accurate. They're considered to be good. So real deal. So this is the real value, let's say, the actual value, if you can call it that way. And then in this plot, what you're going to see is the accumulation of measurements. Red dots are going to be measurements by Android phones, while blue dots, similar to what you did, are going to be measurements by iPhones. And then we have the standard deviation and means of these plots. And remember, the blue triangle is going to be the average, or the spatial center point or midpoint of the iPhone measurements. The red triangle is going to be the same thing for Androids, and the green one is just the average of everything. On the bottom, you have a box that just tells you the number of points of individual. Like you have one, that means one Android measurement and one iPhone measurements. On the right hand side, I have two rows of plot. On the top, I have iPhone measurements, and at the bottom, I have Android measurements. The left column is for longitude. So these are histograms, the number of points binned, let's say, over fractions of degrees in longitude and latitude. So the first one is that, the histogram of longitudes and the histogram of latitude is on the right. So you add you try to make a movie of this. As I add the points, the measurements by the students recorded in that online document, you get this, which is kind of neat actually, because almost none of them actually coincides with the yellow star, or very few of them do. And you plot these on the histogram, you see, on latitude, while you see they're both doing fine, they're peaked around the center. On longitude, androids are doing much better. So androids, I would say, on latitude are more accurate and more precise because they're clustered, and they're clustered in the center. Whereas iPhones, not so good. They're not doing so well because you can see they're clustered, but the cluster doesn't coincide by the yellow line. Now remember, we're not generalizing this. We're not saying like androids are better phones than iPhones. But the point we're trying to make is that different instruments can treat the same signal differently, and how your measurements can be biased by the kind of instrument that you're using. Also, this gives the students an idea of the uncertainty in their measurements. The values that you can see, scribbled in the plots, they're actually the uncertainty, the final, let's say, uncertainty in their measurements. So these two were the two kind of activities that we tried to make our case with about, on using smartphones in our science classes, and try to find out whether or not they were, doing fine. And we found out that we were doing actually a great job. But remember, you can't. I mean, you're only limited by the boundaries of your imagination. There is a whole bunch of stuff you can do with your smartphones. Well, you can direct your own movie. You can record a movie. Well, just you have to watch for the colors, because obviously you don't want the whole picture to be like, look bizarre. You just want it to look gorgeous. And then you have to be creative by just, shooting different things and, sort of pasting them together. And you don't really need to do anything on your computer. You can process the whole thing on your smartphone. For example, a famous case in neuroscience classes is measuring g, the acceleration due to gravity. And while discussing that topic in the class, the first thing that usually pops up is the pendulum. And the pendulum, you argue that you can measure the period of the pendulum with physical means. Now the question is, which of these two pendulums swings more quickly, swings faster or longer? Well, they're of the same length and of the same mass, but the top one is starting this oscillation at the larger angle. So which one would you say has a larger period? Well, thanks to Mr. Galileo, we know that the period is given by this sort of equation that only depends on the length of the pendulum as well as gravity of the Earth, which is just an acceleration, 9.8 meters per second squared. Well, so the angle shouldn't matter, right? But that right is a big question. You can't really accept that unless you see it. Well, when you're doing the demonstration, like with the real pendulum in the class, the students see this, but the pendulum is usually going too fast. The students cannot really see anything. So what I said, okay, why don't I try to recreate this and replay that in a slow-mo? And here's what I got. So on the top one, again, I have the same thing, and I've just the red line, sort of marks the equilibrium point, and bingo, the period is the same. So students can always see this, and this is not an activity that you do in the class, although you can include it as an activity if you tell them how to make the movie. But if this is on the teacher's side, if you show them this, I mean, it's then and there. I mean, it's obvious. So again, smartphones have a whole bunch of capabilities that you can take advantage of in your classes. So what's up next? Well, we published this in December 2017, and the paper got a sort of positive reviews, and people seem to like it. We always ask ourselves, well, publishing doesn't mean it's finished. You have to try to expand on what you've already done. And remember, uh, this is, I mean, I usually don't like adding conclusion slides to my presentations, but well, this one serves as a conclusion slide. So this is a famous quote. This is a really interesting quote by Elias Schulman. Um, and he says, well, every educational idea is inherently incomplete and probably seriously flawed. An idea is useful to the extent that it can stimulate the thinking and scholarship of others. Now, remember, uh, you can design all kinds of strategies, but you can never be like, wrong in teaching, even though your idea is incomplete. You can teach, and you can always be creative in your teaching, and don't be afraid of, making mistakes of, you know, I'm using this new technology, it might go wrong. Well, so what? I mean, you can always take advantage of the loopholes in your experiments, for educational purposes. So I'll leave you with this quote here, and what I just want you to think about is that, why should you stop? Why should you not give it a shot? Try to use smartphones. You won't regret it. Thank you.